Hello class, today's lesson is chemical properties of alkyl halides. In our previous topics, we have studied alkyl halides and how to name them. We defined the alkyl halides as derivatives of hydrocarbons, in which a hydrogen was replaced by a halogen. We have also talked about classification of alkyl halides, where the main classes were primary, secondary, and tertiary alkyl halides. We have studied isomerism of alkyl halides, mainly position and chain isomerism. We then talked about the physical properties of alkyl halides, focusing on physical states, solubility, density, and boiling and melting point. And today, we are going to continue with the chemical properties of alkyl halides, starting with substitution reactions. Precisely, we are going to talk about nucleophilic substitution, where a nucleophile replaces a halogen, which is a living group, from an alkyl halide, which is a substrate, to produce a new molecule. A nucleophile is defined as a chemical species that donates a pair of electrons to form a covalent bond. Here we have two chemical species. We have Nu negative and another molecule which have X element, and that X is representing halogens. The halogen is more electronegative than carbon. Because of that, the halogen is withdrawing electrons from carbon, and that acquires a negative charge on it, while carbon is acquiring a partial positive charge. Because of the positive charge on the carbon is attracting electrons from the nucleophile to form a covalent bond. But this pair of electrons is going to repair the pair of electrons between carbon and the halogen and make the bond break, where the formation of a halide ion and a new molecule. This molecule, which is rich in electrons and donate electrons to the substrate, it is called a nucleophile. While the substrate is this molecule which contains the halogen to be substituted by the nucleophile. And the halogen, which is going to be replaced by the nucleophile, it is called a living group. During the nucleophilic substitution, there may be inversion of stereochemistry or retention of stereochemistry, or a mixture of both, depending on the type of mechanism. Introduction. The chemical reactions of halogenoalkanes mainly depend on the following factors. The first factor, the halogen atom present on the halogenoalkane structure. It means that the ease of reaction depends on the ease of breaking carbon-halogen bond based on the size of the halogen. Second, it will depend on the position of the halogen atom within the molecule, which means that tertiary alkyl halides, they are more reactive than secondary alkyl halides than primary alkyl halides. Order of reactivity of alkyl halides, which have the same carbon chain but have different halogens in the chain. The order of reactivity of various alkyl halides towards nucleophilic substitution is like this. Ri is more reactive than Rbr, more reactive than Rcr, more reactive than Rf. As this table shows it, the order of reactivity depends on the strength of carbon X bond. The carbon X bond is the weakest in Ci and the strongest in Cf. In fact, the Cf bond is so strong that organic fluorides do not undergo nucleophilic substitution under ordinary conditions. Here the reason is, if you look at the bond lengths, you can see the carbon iodine bond it is the longest, while the carbon-fluorine bond is the shortest. But if you look at the bond enthalpies, which is the energy required to break the bond, we see that the carbon-fluorine bond requires much energy than the rest of the bonds, while the carbon-iodine bond requires the least energy compared to the other bonds, which means that a bond which is long, it is weak, while a bond which is short, it is strong. We have our first reaction of halogenoalkane with sodium hydroxide or potassium hydroxide. If halogenoalkane is heated under reflux with a solution of sodium or potassium hydroxide, the halogen is replaced by hydroxide ion and an alcohol is produced. You can ask yourself, what is heating under reflux? Heating under reflux means heating with the condenser placed vertically in the flask to prevent loss of volatile substance from the mixture. Here we have examples. We have bromoethane, iodopropane, and we have chloromethylpropane, which all react with strong bases to produce alcohols. If halogenoalkane is heated under reflux with a solution of sodium or potassium hydroxide, the halogen is replaced by hydroxide ion and an alcohol is produced. You can ask yourself, what is heating under reflux? Heating under reflux means heating with the condenser placed vertically in the flask to prevent loss of volatile substance from the mixture. Here we have examples. We have bromoethane, iodopropane, and we have chloromethylpropane, which all react with strong bases to produce alcohols. Let us have a mechanism involving bromoethane, which is a primary alkyl halide, with a hydroxide ion. A primary alkyl halide, as you know, it is an alkyl halide in which a halogen is attached on a primary carbon. And the hydroxide comes from a strong base like sodium hydroxide. The sodium hydroxide is going to dissolve in a polar solvent like water and produce hydroxide ion. Here we have two chemical species now. We have a hydroxide ion, which is a nucleophile, and we have a bromoethane, which is a substrate. As we saw it in the previous explanations, the bond between halogen and the carbon, they are polar, and the carbon has acquired a positive charge because of electron deficiency due to high electronegativity of a halogen. So this positive charge of carbon will attract electrons from the nucleophile and form new covalent bond. But this pair of electrons will repel electrons of the bond between the carbon and the halogen and make the bond break to produce a bromide ion and an alcohol molecule. So this will be the mechanism of the reaction between bromoethane and the hydroxide ion. The name of this mechanism is SN2, where S stands for substitution, N stands for nucleophilic, and 2 stands for bimolecular. The full name is nucleophilic substitution of the second order or bimolecular nucleophilic substitution. What does it mean? Because this mechanism involves collisions between two species in the slow step, in this case the only step of the reaction, it is the reason why we call it bimolecular. Bimolecular means two species are involved in the rate determining step. Let us use the expression of rate of reaction to explain this. The rate of reaction is calculated using the concentration of chemical species involved in this reaction. We say that the rate of reaction is proportional to the concentration of chemical species involved in the rate determining step. And here the two chemical species are the substrate and the nucleophile. The order of reaction with respect to the substrate is 1. And the order of reaction with respect to the nucleophile is 1. So the order of reaction with respect to both substrate and nucleophile is 1 plus 1, which gives 2. That's why the rate of reaction, the order of this reaction with respect with both substrate and nucleophile is 2. And the name of this mechanism is SN2, nucleophilic substitution of the second order. A potential energy profile diagram can help us to understand what happens in terms of energy. Here we have two axes, y-axis which represent the potential energy and x-axis which represent the reaction pathway. As it is for all reactions, we start with reactants which have a given energy. But during the reaction, the energy can rise and reach to a given point and falls again to form the product. The peak of the graph is representing the transition state, and the energy required to reach to the transition state, it is called activation energy. In fact, activation energy is the minimum energy required to start a reaction, while the transition state, it is the highest potential energy along a reaction coordinate. For our reaction, because it is happening in one step, it will have only one transition state, thus one peak. Mechanism involving 2-chloro-2-methyl-propane, which is a tertiary alkyl halide with the hydroxide ion. I want to remind you what is a tertiary alkyl halide. A tertiary alkyl halide, it is an alkyl halide in which a halogen is attached to the carbon, which is also attached to 3 other carbons. During the substitution reaction, when this alkyl halide is dissolved in a polar solvent, it undergoes self-ionization. It means that the molecule itself can lose the halogen and form a carbocation ion. This is possible for tertiary alkyl halides because of the stability of carbocation formed. What makes this carbocation stable? It is the positive inductive effect from the alkyl groups which are bonded to this positively charged carbon. Through hyperconjugation, the negative electrons neutralize this positive charge on carbon and make the ion in general somehow stable. But we cannot say that the carbocation is fully stable because you can see this carbon is having only 6 electrons around it, while it was supposed to have 8 electrons around it, which is octet stability. Because of that, it still has this positive charge, which will attract electrons from the nucleophile and form a dative covalent bond, which will result in the formation of an alcohol molecule. Now, you can see the difference between a primary alkyl halide and tertiary alkyl halide when you look at their mechanisms. The primary alkyl halide undergone only one mechanism, only one step in its mechanism. But this tertiary alkyl halide has 2 steps. And then we want to know which type of mechanism is this. We saw that the primary alkyl halide undergone SN2 mechanism. But this time we have two steps, and we are going to choose one step, which is the slow step, also called the rate determining step of the reaction, and we look at how many chemical species are involved in that step. And here it only involves one species, which is the halogenoalkane or the substrate. So this one will be called SN1 substitution. Now you want to know which step and why I have chosen that step as the rate determining step. Comparing the two steps, you can see the first step is requiring much energy compared to the second step for it to give the product. To break the bond between carbon and chlorine, it is high endothermic process compared to the attraction of positive and negative ions of the second step. So, because of that, we can say that the first step is going to have high activation energy to reach to the transition state than the second step. Let us use a potential energy profile diagram to explain the type of mechanism in this reaction. As you can see, we start with the reagents with a given energy and we produce products with a low energy. But this reaction happens in two steps. The first step will form transition state 1, and the second step will form transition state 2. In the middle, we'll have an intermediate carbocation. What does it mean? It means that the tertiary alkyl halide will first undergo self-ionization and form a carbocation. But it will first form a transition state 1 where the bond will not be completely broken in order to form a positive charge on the carbon. The carbocation formed will attract the electrons from the molecule of hydroxide ion, and this one will form a transition state 2 where the bond of oxygen and carbon will not be fully formed, and this one will acquire another energy. So to know which step has taken a long time or which step is longer than another, we are going to compare the activation energies. For transition state 1, we have activation energy 1, and for transition state 2, we have activation energy 2. So we just need to know which energy is much higher than another. When you look at the activation energy 1 and activation energy 2, you will see that activation energy 1 is much higher than the activation energy 2, which means that the first step required much energy compared to the second step. So the first step is the rate determining step, while the second step is not the rate determining step. Looking at the type of mechanism, we are going to consider only the rate determining step, which is the formation of carbocation. Let us look at the expression of rate of reaction of this reaction. Then the rate of reaction is proportional to the concentration of the substrate, which is alkyl halide. The order of reaction with respect to the concentration of alkyl halide is 1, and it is the only chemical species involved in this reaction. So we are going now to have the rate of reaction, which will be SN1, which means that it is nucleophilic substitution of the first order because it is only depending on the concentration of one chemical species, which is the substitution. Mechanism involving 2-iodopropane, a secondary alkyl halide with the hydroxide ion. The facts of reaction are exactly the same with the primary and tertiary halogenoalkanes. The conditions of heat and solvent are the same. But which mechanism is undergone by a secondary alkyl halide? Is it SN1 or SN2? Feel free to pause the video and answer the question. Let me give you a hint. Primary alkyl halide undergo SN2 because they cannot undergo self-ionization. Tertiary alkyl halides undergo SN1 because they can undergo self-ionization, but the nucleophile cannot attack because of steric hindrance. So what about secondary alkyl halide? Is it SN1 or SN2? The answer is secondary alkyl halide, they can undergo both SN1 and SN2 mechanism. It will just depend on the conditions. Let us start with SN2 mechanism. The alkyl halide is having poles as other alkyl halides we saw before, and the carbon is partial positive while iodine is partial negative. The positive charge on carbon will attract electrons from the nucleophile, and these electrons will repel the electrons of the bond between carbon and iodine, which will result in the formation of iodide ion and an alcohol. This is the first step. Is there any other second step? No. Because the substitution is over, this is the only step we have for SN2 mechanism. And because there are two chemical species involved in this only step, it is the SN2 mechanism. SN1 mechanism, here we will follow the two steps. The first step is self-ionization to form a carbocation. And this carbocation, the positive charge on the carbon will attract electrons from the nucleophile, which is a hydroxide ion, and this forms an alcohol. There are two steps involved, but one of them will be the rate determining step. And which one is that? It is the first step, the formation of carbocation, because it is high endothermic compared to the second step. Conclusion: primary alkyl halides undergo SN2 only, tertiary alkyl halides undergo SN1 only, secondary alkyl halides undergo SN2 and SN1. Primary alkyl halides cannot undergo self-ionization, but the electron-deficient carbon is less hindered. Tertiary alkyl halides can undergo self-ionization because of stability of carbocation, but electron-deficient carbon is much hindered. Secondary alkyl halides, they are there in the middle. Activity 1. Pause this video and try this question. After, go back to your notes and correct yourself. Thank you.